Awesome. Then I guess without further delay, we'll get started. Hi guys, I'm Greg. I'm a senior software engineer at Interlay. I've been working for around 2+ years now, core parachain developer and...
You can have
What was that? Okay, yeah, core Rust developer on the Btc parachain and the associated Vault client, which I'm going to talk through a bit today. Mostly Rust, as I said, maybe a little bit of research on the side as well, and product direction. But I've been working with subxt, probably one of the most underrated bits of kit in the Polkadot ecosystem for since the very beginning. Okay, now it's doing weird things. Oh, go back. It's not going back. Okay. Oh. Awesome. Yeah. So I'm working with Interlay. We're building into Btc. It's a fully decentralized Bitcoin bridge. We're live on Kusama, and we're also live on Polkadot. I'm pleased to announce that we'll be launching Btc Vaults within the coming weeks. So Btc will be officially live, and trustless Btc will be on Polkadot. We're slowly opening up bridges with channels with other sibling parachains such as Moonbeam and Akala, and we'll be opening up more over the coming weeks and months. So I want to give a bit of like an introduction and background of like kind of how the tech stack for Substrate works, and a bit of context before we get into kind of nitty-gritty of subxt. So we have our Substrate client. This sits on a box somewhere, processing blocks, validating according to the runtime, and it has a few different components that we should talk about here. So the whole kind of bundle is the outer node that handles kind of network connectivity. So we have sort of the P2P layer using libp2p. We have the RPC for inbound connections from users, and we have telemetry for like the Prometheus server. Within the node itself, we have kind of a consensus mechanism. We have storage, so this is the key value database with an abstract of a Merkle-Patricia tree. And we have a runtime. So in this, I've actually separated. We have two runtimes. We have the native runtime, so that's the thing that's built onto the native platform. And we have the WASM runtime. This is the thing that's stored on-chain and enables us to do cool stuff like forkless upgrades. Then we're going to kind of zoom out a bit into more of like how do we look into querying this node. So again, we have this runtime, which is the native or WASM. We have sort of like an abstraction around the runtime called the Runtime API, and this enables us to do forkless upgrades because the Runtime API interface is far more stable and allows us to query things such as storage or blocks. And it also allows inbound connections for us when we want to query the runtime for a specific state. The Runtime API then speaks with the node. This is kind of the back end. This is, we saw in the last slide, where we have kind of the storage layer. This is hosting the Prometheus server, the JSON RPC server, and other components like that. And then we kind of go down to the layer we're more interested in looking at subxt, which is the RPC layer. And this is kind of the interface defined for like submitting extrinsics, reading storage, subscribing to events, and things of that nature. So yeah, just to clarify a bit what the runtime is. The runtime is this kind of kind of the business logic of a parachain. It's the state transition function. It's kind of it's kind of a conglomeration of a lot of different things we call palettes, and I'll discuss kind of a bit more what palettes are in a second. So in the example here, we have maybe the balances palette. Most, if not all, parachains and even the relay chain will have the system module. This is the core types, event handling, etc. And the support palette gives us sort of like enables better palette development and macro support and some other niceties and helpers. As mentioned before, the Runtime API kind of wraps that, and this is kind of like the interface between everything else and the runtime. But it's important to know what's in the runtime when we want to look into palettes and their structure. So we're zooming in even further here. But what is a palette if not a collection of these 5 things? Storage, again, is like the interface between what's stored in the database and what we reference in our runtime module. Extrinsics are the things that we sign in order to move that state transition function on. Events are more like notifications for downstream systems. Subxt leverages these quite significantly for a lot of its processing. We then have constants, so these are fixed values, and errors that describe the things that could go wrong. So palettes are more or less the building blocks of substrate and runtimes, and it defines usually you kind of group common related functionality and specific types and things of that nature. And one thing I would like to mention is sort of type info and self-descriptive types. And this is particularly important in the newest incarnation of subxt, which allows us to do more code generation and compile type assertions on what we expect to be reading and writing to our node. On the wire, speaking to the node, so we've mentioned this RPC layer. We want to look specifically Substrate utilizes JSON RPC 2.0, so kind of have a method and parameter syntax. JSON RPC, of course, is a lightweight kind of RPC protocol for defining it defines several data structures and kind of protocols around their handling. With JSON RPC 2, we also have kind of the kind of traditional method of communicating over JSON RPC is HTTP. The default port for that is 9933. But you'll find within the Substrate ecosystem, we leverage WebSockets quite significantly. This is a non-standard layer around JSON RPC that allows us to do far more powerful things with regard to polling and subscriptions. And we receive push notifications from the node itself when state changes. So I have an example of JSON RPC, which I'm going to go into in a minute, but I also want to touch on scales, the other important thing to know about. So scale is the kind of encoding standard used by Substrate, most parachains, and the relay chains. And it's just basically a binary, all you need to know about it is it's a compact binary encoding standard. And it's quite light, and it's used for storing most data stored and transmitted by the Substrate client is encoded with scale. So to kind of wrap sort of the introduction up here, let's look. We have JSON RPC. We need to connect. That's what we need to use to connect to a node. Mostly everything is encoded with scale. I put a little asterisk here because many of the RPCs use simple JSON encoding. There's some issues with that. With Rust, we use a library called Serde. And lastly, the metadata tells us sort of the runtime structure of what our palettes and runtime looks like, and how we want to interface with that. So to go back, this is a bit of an example of like how you would use the JSON RPC manually, for instance. So it's just a curl to read the metadata. In a bit, we'll see there's a small tool, a CLI from subxt to download this metadata, and it basically just does this. We fetch this directly from the node using the HTTP provider, and then just a little snippet here saying, okay, it returns a hex-coded result, and then we decode that into this runtime metadata, which we can then use for some cool stuff in a bit. The other thing I want to also show you a bit is kind of reading storage. This is the classic example of interacting with a node manually. Doing a state get storage. In order to retrieve the right key value from storage, we need to build the appropriate key name, and this is what subxt handles for us. We take the module name, the concatenation of the module name and the storage name for reading a storage value, but if we were to read a storage map or a double storage map, we might truncate additional fields on top of that. And again, subxt will handle all of this for us, but it's worth knowing that's what's happening in the back end. So this builds us finally to what we want to get out of this workshop, which is how do we build clients that interact with Substrate. And we can use something called subxt. You can see that's a kind of concatenation of submit extrinsics, but obviously it can do far more than just submit extrinsics. Lower level, we use a cool library called JSON RPC. And with I also want to give a quick shout out to a few of the core devs that have been very helpful in building this set of tech. So I think one of the kind of original founders of subxt, who's doing it in his spare time, was Andrew Jones. James Wilson's since taken it over, and Niklas Adolfsson is doing kind of the JSON RPC layer, and now that's even, I think, integrated into Substrate Core. So that's at all layers of the stack now. We can get async JSON RPC reading everywhere, which is awesome to see. And my colleagues Dan, Theo, and Sander have also been great in kind of working with and helping contribute to subxt. So also shout out to them. So yeah, subxt, this is the toolkit we're going to look into. So like Substrate, it's using macros to generate code, particularly client-side code. So going back to the metadata we downloaded, we know the structure, we also know the types, and we have some cool stuff with self-descriptive types, which enables us to build Rust codes purely from metadata. So for this we use procedural macros, and we can then build that at compile time and assert that the structure of the node we interact with is as we expect it. So yeah, in addition to this, it handles all the encoding, decoding, and networking, so it kind of takes away any kind of rough edges there for client-side developers. But before I kind of get into sort of the developer workshop, I want to spend a bit discussing Btc Vaults and what we're doing at Interlay to use subxt and issues we faced and things other consumers may want to consider when they're developing their client-side software. So what are vaults? Vaults are our answer to the transacting between Bitcoin and parachain. Specifically, in our case, the Interlay Polkadot parachain and the Kintsugi Kusama parachain. Vaults are collateralized intermediaries, and they have a number of functions, both incentivized and non-incentivized. The incentivized being the custody of Bitcoin on the Bitcoin network, and proves to the parachain that they have transacted in a manner of which we expect. So the core, at its core, the primary thing we want the vault to do is receive Bitcoin and send that back when there's a request in order to have a wrapped fungible token. So we have a couple of mechanisms on the parachain for that. I wouldn't spend too long, but we have the notion of issuing. This is like a two-phase commit in which a user would send Bitcoin to a Vault's registered address. The Vault receives that in his wallet and should then out of bounds track how much fees it needs to pay and where that UTXO it lives. Then also we have this function here we're more interested in this case is redeeming. So when in order to have a fungible token, Bitcoin or the wrapped asset, so KBTC or IBTC needs to be burnt on the parachain side and redeemed for physical BTC on the Bitcoin side. In order to do that, the Vault needs to listen to what we would call redeem requests. So it needs to subscribe to a certain type of event on the substrate side that tells it should transfer that Bitcoin in accordance with the logic there. As part of the two-phase commit, we want it to send that Bitcoin and provide a Merkle proof to the parachain. We have a light client in the parachain, which that will prove that it sent the Bitcoin to the user's address. This light client also needs to be maintained. The Vault client in a non-incentivized action is required to submit relayed block headers. And it also confirms issue requests from other users as a best effort. Lastly, the more important thing, which is going to kind of come up on the next slide, is theft reporting. So vaults are liquidated if they don't, if they mishandle Bitcoin. So if Bitcoin is spent without a approved condition on the parachain side, then they forfeit their collateral holdings, and that's how the Xclaim protocol is designed. So yeah, stands to reason that the biggest issue for us when developing a Vault client is bugs and the mishandling of that logic. And indeed, most of the cross-chain hacks we've seen in recent times have been down to mishandling of the connection between the two ends of the bridge. So these are some of the biggest, more fun or interesting bugs we've encountered over the last number of years through our testnet phases, mostly in relation to liquidation and the mishandling of Bitcoin. And these are issues specific to our development with subxt and things we kind of didn't realize or did wrong. A bit later in the workshop, I'll kind of go into more descriptive ways that you can improve your developer experience with subxt. But these kind of summarize a few of those right now. So the first issue we see here, we discovered that by default subxt doesn't listen to finalized events. So blocks are produced and they're not immediately finalized. So we've discovered that simply subscribing to events, we listened to blocks that were reverted, and we acted on information which was no longer valid. So this meant that if we were to already process the payment of Bitcoin on the Bitcoin side in accordance to an event which no longer existed, well, that vault could be liquidated for theft. Likewise, we discovered we had some restart logic, and we discovered that vaults process duplicate events on restart. So whenever the vault failed and would restart, we would subscribe to a previous block height, we would just subscribe to the current block height, and that wouldn't always take +1. It might accidentally reprocess events as processed. And one of the things I should have mentioned with the Vault client is it is stateless. So it's based on data it reads from the parachain and the Bitcoin network. We're looking into changing that, but this we decided to. I think we always wait for the next block now in order to keep processing. But this was one of the main issues we faced early on. Lastly, we found a more interesting one. Again, with sort of our handling of reconnections and restarts. So we found that on restart, we didn't disconnect child tasks. So one of the things I'm going to mention, sort of like the best practices, is to look into sort of the handling of reconnects and fallible services, of which Substrate RPC may be one. And what we did here is we would restart our internal Vault service, but we'd fail to disconnect child tasks which were already processing Bitcoin payments. So we lacked a bit of atomicity there. And what that meant was that if you were unlucky with timing and the JSON RPC disconnected at the right point, then the mutex on the Bitcoin transaction may not have been made yet, but it may have been about to be processed, and we may have missed that payment being made before we already went on to the next Bitcoin payment. So that was an issue there, and we discovered that a few vaults were liquidated on our testnet due to that bug. We're doing some more interesting stuff at the moment. We're adding, like with Substrate, we're adding Prometheus metrics, so vault operators can monitor exactly what their vault is doing. We also have a new kind of best effort transaction submission policy based on user feedback, so we don't always, like the relay, for instance, it submits relayed blocks on a best effort basis, and what we did there was, in order to save on wasted transaction fees, we had an outer bound kind of decision on when a particular vault should try and submit like a Bitcoin block or some of these best effort transactions, so it wasn't kind of spamming the chain. And we've also kind of improved our versioning and timeouts, so we have better retry policies there. The next steps for us is to actually make the Vault client stateful. And this should alleviate a lot of the concerns we've seen over our earlier phases and even on our Canary net. We also want to subscribe to Runtime Upgrades. Currently, forkless Runtime Upgrades give us a bit of a pain on the Vault side because everything is native, which means that we can't really upgrade on the fly. There's a lot of operations that we require statically compiled interfaces for. So what we're going to look into is, first and foremost, actually, we're going to look into sort of building a sort of a visor process that automatically upgrades the node in accordance with the parachain logic. We're going to store maybe binary links on chain to GitHub releases. But in the far future, what I would really like is some sort of substrate-based like architecture where we have kind of the runtime of the vault stored inside the vault, which can be downloaded directly from the parachain on a runtime upgrade, and have sort of a seamless forkless upgrade process there. The other thing kind of mentioned there is instant seal. Currently we're using quite a slow testing process, so we want to speed that up. So that kind of brings me now on to subxt and kind of more the developer process and what you should know before you get stuck in. And there is a workshop at the end of this, so you can use the information I present over the next half a dozen slides. In the workshop, we have, I think I built like 10 or so challenges, which I'd love to have people give a bash at, and that kind of gives you the kind of starting run at subxt. So we'll quickly go through the requirements and basics of subxt before we get to that workshop. What do we need to work with subxt? Rust, that's what it's built in. So we use that, download that, and we also need the runtime metadata. So I mentioned before, subxt ships with a CLI that we can use to automate the process of downloading and decoding the metadata, which is used for code gen. So I'd recommend doing that. You can also do this manually. I wouldn't recommend that. But it is required for the next step, which is initialization or the module annotation. So subxt introduces more macros as a derived procedural macro for building the interface for speaking with the node. So what this means is that at compile time, it tells Rust to build sort of data structures and functions and helpers and kind of niceties on how to speak with the substrate nodes that the metadata is downloaded for. However, with kind of the new kind of runtime metadata v14 and the self-descriptive types, we may not have some of the niceties of the source implementation, so we can substitute some types. In this case, we're importing the H256 type directly from SP core, and we substitute that in during the code gen, which means that when you go to utilize anything that generates a hash or 256 a hash, then we can use custom implementations derived on the source implementation. We can also add custom derives for the auto-generated types. So we can see we have a few kind of ways to do that. We can derive for all types. So for in this example, I'm deriving equal and partial equal for those Rust traits for most types auto-generated by subxt. And we can also derive for a specific type. So in this case, for the balance type, I want to derive order and partial order. It won't do anything because, in the end of the day, alias is directly to Rust built-in. But in this case, it's interesting to reference, and that's all compiled at compile time. Now we're looking to how we actually build and connect our subxt client. We can import the client builder from subxt source, and then that will, I think that by default uses the WebSocket connection, because things such as event subscriptions and transaction inclusion verification is not possible to do via HTTP. I'd also mention that the client, subxt use itself is generic, so you can do some pretty cool stuff. You can replace that with anything. It doesn't have to be a live node. It doesn't have to be a WebSocket provider. You could build your own interface there. In fact, in our toolkit for testing, we use an embedded node. So because Substrate is built in Rust and subxt is using Rust, we can kind of cut out the middleman of having to initialize WebSocket connections and doing networking there, and just speak to a node directly. And that, I believe, in our case, makes testing easier, because you can always clear the state after the end of each test. It was all on startup. It will also fetch the metadata dynamically. This is in order to check compatibility. So we may actually want to validate the metadata on startup. We may not want to if for whatever reason. But the purpose of this is then we can fail early if we're speaking with a node in which we don't have the right descriptive API of. Okay. So now we kind of get into what can we do with the client. And the first thing I'd like to draw on is reading storage. So I should mention that with subxt, everything's kind of derived for you at compile time. And we have like a reference to the client in some of these APIs. So the runtime API is fetching the storage API, which is in a child module of the auto-generated code there. And then in order to fetch a storage name, so unlike the manual example I gave earlier, where we have to derive the storage item manually, we can subxt CodeGen actually gives this for us, so we can actually call the palette and the storage item name. So a hint for one of the workshops, I think, is that in one example, we might want to fetch the balance of an account. And what we do here is the palette name in that case might be balances or even system. And then the storage item would be accounts or balances perhaps. And we might, in the kind of arguments here, again, if you have a good Rust ID, it might give you some auto-completion here, but we would have to give it like an account ID if we were trying to read that storage field, or storage map rather. And the other thing to note is that, sorry, I have notes because there's a lot to know about subxt, is that we can also give it the block hash. So we might want to query the storage item at a particular block height, and this will work if you have a node that stores multiple block headers. It might fail if the node is somewhat pruned. Most storage reads allow giving this block hash. Indeed, most RPC calls also allow specifying the block hash. And that's, I think that's quite important to know. You can, with the kind of Rust CodeGen here, you can actually give it none, and it would, the subxt kind of API would just fetch the latest block hash and use that. Or indeed, actually, I think actually it would encode to null, and Substrate would interpret that as the latest height. Unsure if that would be. I think that would always be the latest, so it might actually not be the finalized height. So it's something to bear in mind. Another cool thing to know here is another one of the type derivations. So the CodeGen constructions it gives us is _iter, so we can iterate storage maps. This would mean that we don't have to give it an account ID argument, and we can retrieve like a list of data entries in a storage map, for example. And we can also do this for double storage maps, etc. Next up, we have constants. You should all know what constants are. They're just constant, except they're not always. In fact, actually, I think subxt downloads the constants dynamically from the runtime metadata. However, it is advised by the static CodeGen, so you know what to point to when you're coding in Rust, and before that binary is compiled. Next up, events. So we can actually subscribe. In this example, we are querying events at a specific block hash. Again, this may or may not fail, depending on how many if the node is storing enough blocks. But then in this example, we just collect all the events in that block. We could do whatever we want with those. For event subscriptions, these are more interesting things for downstream development. We can subscribe to all one or multiple events. In this case, we're subscribing to this runtime palette events event. So a single event, so each poll of the subscription here will print that of the event. It's worth noting that subscribe here is also subscribing to latest blocks, non-finalized. So if you want to listen to finalized events, you'll need to tag on _finalized. Excuse me. And events are dynamically decoded, so the polling here may fail. I think actually in this case, I've got it wrong. Event is a result, so we'd probably want to to handle that, but it would anyway just print the result there. Now, the main matter of subxt is to submit in extrinsics. So for this, we need a signer, which we haven't needed before. We can use a number of different crypto primitives for that. I think the default one I think is supported is SR25519, Schnorkel Ristretto. And we can construct in this case, we can use the default kind of set of testing accounts. So we can use Alice. And that's used then to encode and sign the transaction. This will, we can see here we're waiting for finalized success, so this is waiting until the event is, so the transaction is actually included in a finalized block, and the result of this is something called transaction events, and that will actually contain all the events output by that extrinsic, which is quite handy to filter over. And then lastly, we can also use subxt to make a custom RPC. So under the hood, subxt is doing exactly this with all the other stuff, just making it look nicer. But sometimes you may want to make a manual call. Again, you can give it a block hash. So in this case, I've given it subhead. We give it the method, and we encode the parameters as it expects. Okay, and then that brings me to my conclusion. subxt loves macros, as does Substrate. So we're not seeing any less use of macros across the ecosystem. But they're pretty handy, and they make our life easier when we're building the Btc Vault client. Some things I didn't cover, I kind of glossed over, but might be important to you, is custom configurations. So there are some static types required in embedding your client logic. For this, you will need to give it. So a good example is like some of the core types and things required by extrinsic construction. So for instance, one of the default configurations subxt requires, Polkadot, I believe, uses the assets palette for tipping. In our parachain, for example, we don't support that, so we might see the WASM trap error because the extrinsic is constructed the wrong way. So we require building this convex slightly differently. Some other cool interesting stuff is like paging storage keys, so we don't have to fetch the whole storage at once or even over time. We can just page entries gradually like we might do with a typical Postgres database or so. We can also read double storage maps. I think I did actually touch on that a bit earlier. Some more interesting stuff you might want to work on if you're looking into subxt. I mentioned that we have like an embedded node. You can build that yourself. I can show you if anyone's interested how we do that with our Inter-Btc clients. But some more cool stuff. Actually, one of the workshop exercises will touch on transaction fee estimation and ask you to kind of implement some helpers to help you use subxt to estimate the fees of a transaction. And also dry running. That's I think, reasonably newly introduced RPC on the Substrate side, so we can basically construct an encoded signed extrinsic and test that the result of that would succeed, or see how the state of the system is affected before we actually submit that to the mempool. I think with the kind of summary of the Btc Vaults, I already touched on some of the risks you may face in client development, the first being finalization. So I think in the developer guide, I touched on a few points where you might want to check for finalized versus non-finalized. It's obviously, there's no default, since the consumer may want to do different things depending on the end goal. But it's worth noting, if you're acting in response to system events, you'll need to check that those are finalized, or those blocks are finalized. Another problem we've seen is transaction mortality. So the transactions maybe after they're submitted, they may be forked. So for that, you can actually, I should have mentioned this actually in the extrinsic construction, but you can give certain parameters, which includes a tip, and also the transaction mortality, so you can say how long you want that to be valid for. In lack of this, you may also want to just reuse nonces or do better nonce handling. I'll also touch on that in a second. But that should prevent additional transactions getting in when the original ones may still be included that failed. We've also seen a number of bugs with JSON RPC and then subxt by relation is timeouts, and if you're doing particularly CPU-intensive tasks, so on our end we were obviously subscribing to events and then interacting with Bitcoin, which is inherently slow. That caused us to not read a lot of streams in due course, and buffers would often fill up and kind of fail on the client. So it's worth noting that you might want to make sure that these aren't blocked in any way, and you can continue polling and running your logic against those. I think this also refers to like timeouts in general, and just making sure that you don't retry too early. So these are sort of some tips and tricks that we've kind of come across. So error handling, all services are fallible. You may want to consider more resilient built-ins. So we have sort of now reconnection logic. This has caused us a few bugs, but at the end of the day, if our Vault service is meant to be running 24/7, 365, then we need to make sure that that doesn't, when that fails over, it's for a bloody good reason, and that can keep processing events despite issues with the parachain. The transaction nonce, as I just mentioned, we may want to track that and increment it or keep it the same in certain situations. So if you're resubmitting an extrinsic that potentially failed but may still be included, we may want to reuse that nonce. But in the case you're submitting concurrent transactions, I believe there's a bit of handling in subxt now for this, but you may want to track that in your client consumer and increment that after each transaction, so you could submit multiple to the mempool at once, for example. And lastly, data freshness. This also, I think, kind of relates to kind of the transaction nonces and tracking that, but you should consider when to cache data, especially when acting on stale data can be costly. One other thing we want to do with the Vault client actually is to dry run all transactions before submission. And this is that's also an important point, because then we don't have to worry about checking that the transaction or the inputs to a transaction are valid, but we instead can just assume it's valid and test it through dry running. Some things I'd like to see with subxt and also Substrate, I guess, RPC metadata. So currently it's the process of adding RPC calls to subxt clients is particularly manual. We have to go through the interfaces and redefine the types and encodings there, which is slightly annoying. There's a long disputed open issue I can point people to if they're interested, but I'd love to see some work on that. We also would like some RPCs for like subscribing to storage changes, and so we can do some interesting stuff there. And lastly, we have some services we would kind of want to disconnect so we can allow like concurrent submission and watching. Currently, it's not possible to sign and submit a transaction without directly watching for the result. What we'd like to see is some way to submit that through maybe an external service and watch the extrinsic ID or hash, but that's currently not possible, unfortunately. And with that all said, I'd like to move on to the workshop. It's a bit of a weird format, so I don't know how this works, but I have built some code which you can go to here if you follow the QR code, or you can clone the repository, and that has some cool Rust challenges with subxt. I think there was around 10 I added, so feel free to get stuck into those wherever you're based, and happy to have a look over any problems or challenges you have with that, and thank you for listening. I think there's a question. I don't know if we're taking questions.
We are definitely taking questions. Yes. Way over there. A person who's been here before.
Hi. Yeah, thanks. So I have like a twofold question. So one is that, so basically we already have an official SDK, which is Polkadot.js, JavaScript SDK. So I wanted to know how is this then related to that, because most of the API, let's say, querying a value from a storage of an RPC node is already done in a certain way in Polkadot.js. And here I see that it's done a bit differently. And second, if you have actually considered building, because we might probably need SDKs also in other languages, so whether you have considered building like a core framework, maybe compiled in something like WASM and build then wrappers on top of that.
Sorry, could you repeat the questions? I think the mic was a little muffled.
Yeah, so the second part of the question is whether you have considered building this as a core component on which then other also languages can actually build on top.
So it's building what as a core component, sorry?
Like this library, this RPC library for substrate nodes.
I think we're kind of given everything for free by subxt, and it kind of contains everything we need to build what we need to build. I can't see any reason to fork it and build additional stuff ourselves. Is that the answer to the question?
So yeah, my question was whether I could use another language.
Another language?
On top of subxt, basically. Right, yes. Instead of building the whole subxt in a different language, whether I could build on top of subxt.
Yeah, I don't see a big reason to extend it at the moment. But it might be something, maybe we can chat after. Be interested to hear how you envision that looking. But yeah, thank you.
Okay, thanks.